This sequence of videos corresponds to the second section of Chapter 6, which is titled Using Newton's Second Law, and we are now doing things very similar to what we did in section 6.1, but 6.1 was the equilibrium model. We were drawing free body diagrams, talking about acceleration and net forces for objects that were either not moving or that had no acceleration because they were moving with a constant velocity. Now we're going to generalize that more. We are actually going to talk about acceleration that is non-zero. Part of this requires us to define a second model. The equilibrium model was only valid when objects were in equilibrium. So now we're going to define the constant force model. I am going to again sketch through the beginning of certain problems to hopefully help you get started in doing these calculations. And again, here we have some really important learning outcomes to think about. First is again creating representations, that the way we draw free body diagrams communicates really almost all of the physics that we're thinking about when we think about these types of problems. Now here in particular, we're going to start talking about motion and acceleration as well. So this gets into the idea that there might not be one single representation that you can do to capture everything that's happening in a problem. So now you might want a motion diagram and a sketch and a free body diagram. Lastly, we still have problem solving here to think about because you're going to be using this technique that I talk about in this video to actually do your calculations, to work through these situations and to come to some sort of result. So big topic here, really this is the meat of forces, even though we will continue on for more sections talking about it. So first, Newton's second law. And don't worry about the 6 equations. These are literally 6 ways of saying the same thing over and over and over again. And again, at this point, I'm saying it review because you have seen this in multiple previous videos. So commonly, this would get said as F net equals mass times acceleration. F net equals ma. But there's other ways to write it. So we can rearrange it and simply say that acceleration is equal to F net divided by mass. This is kind of a nicer way to think about it in terms of, say, cause and effect. However, this is the classic way to write it. Then what you can do is break it into x and y components. Now, obviously, instead of it being x and y, it could be parallel and perpendicular if you want to use that coordinate system, which is absolutely fine. And so you can either break this version into x and y, or this version into x and y. So if you were going to simplify this, I think that this is kind of the nicer way to remember the acceleration version. But once you are actually working with components, you're going to usually use these. So again, this might not seem that complicated. However, in many problems, you should actually be writing these down on your paper somewhere and starting from them. If you're doing this first step in your head, it is surprisingly likely that the second step could be wrong. So what I want to point out here is 2 final points. First, that acceleration is something that we talked about in chapters 1 and 2, right? Acceleration is related to motion using kinematics, those equations that had position and velocity and time, for instance. And so those are going to come back now. We're not done with those. So we don't talk about forces and velocity and time, at least not right now. However, acceleration can go back and tie us to kinematics. Second, remember that it's the net force. So again, either F net or writing it as a summation that is determining the acceleration. What you do not do is calculate the acceleration for each force and add it together. That just physically does not make sense. That is not the model we are using. So please do not do that. Okay, so moving on. This is the review. You know Newton's law. Newton's second law. You have this down. Now we get to the problem-solving strategy of Newton's second law. Now, I've broken this into 2 parts just so it will be easier to read on the screen. And this first part is actually something that we've already talked about. So I'm going to talk you through this because it's really important to understand our entire problem-solving strategy. The last few lines of the calculation is not the important part. So first, our model. Model the object as a particle. That's why when we draw it, we typically are going to draw it as just a black dot, and we are going to say that all of our forces act there. We don't actually care if it's a box, whether the force is acting on top or bottom, that's fine. Now then, it says make other simplifications. Note that we're in the model phase. So what might those other simplifications be? Well, that might be recognizing that we're in equilibrium, right? So that might be the model we're using. Another that we're going to talk about very soon is constant force. So part of modeling here is determining which of these two force models you can use. Other simplifications might involve, flat surfaces and so on. So next, visualize. This is your free body diagram, and this is again so important. Free body diagram, visualize. So you also want to be doing something other than a free body diagram if you're dealing especially with motion. And you probably want to do a sketch in general to make sure that you understand what the situation is. So you do your sketch, you establish your coordinate system, you define your symbols, you identify what the problem is trying to find. This is all old, right? This is things that you've theoretically been doing since chapter 1, right? So this is old. Then look, it suggests to use a motion diagram. Why? Because we want to think about the acceleration vector A. If we had equilibrium, we would know that it's 0. It says that in the next sentence. However, in any other situation, you want to find your vector A because that's going to tell you the direction of your net force. Next, we're going to identify all of our forces. So that's when you draw the circle around your object in your sketch and then create your free body diagram. Okay? And again, the book highlights this, and I want to stress this too. It's okay to go back and forth. That as you draw your sketch and your motion diagram and your free body diagram next to each other, you might be going back and making changes. You might want to draw some plots. And again, we might be dealing with situations where you have one period of motion and then a second period of motion and then a third period of motion, such that you might be drawing 3 free body diagrams. And that's okay. So this is the first half of our problem-solving strategy, yet this is where the majority of your physics is. This is also the majority of your points, since this includes both your representation and your modeling. So after this, we have some calculations to do, and that'll be on the next page. So now we solve, and that's where we switch to the mathematical, the quantitative representation, and we're going to use this idea of F-net. Now when it writes it this way, this just means sum over all of your forces, and again, I'm typically writing it, worst sigma ever, as summing your Fx, and that will give you mass times acceleration in x, summing your Fy, getting your mass and acceleration in y. It could also be in z, could be parallel and perpendicular instead. Now, it says something here that again I want to stress, that forces should be read from your free body diagram. That when you actually start writing these out, this should completely agree with your free body diagram. Please don't make the mistake of giving a very poor free body diagram and then going back and trying to do whatever you think is happening here. Once you have your free body diagram down, you shouldn't ever need to look back at the original problem. I mean, you should check and make sure that you're calculating the right thing, but when you do the math, that should be coming from your free body diagram. So now we're getting more to math. What might we be doing? We might be solving for the acceleration, or we might be solving for a missing force based on some other information. That's what it says here. If we know the acceleration, we might then be looking for unknown forces. We might, and I'll be showing this a little bit later in this series of videos, be using kinematics to talk about velocities, time, maybe distance. So force problems can still involve all of that. Finally, please go back, check your units and significant figures, check that your answer makes sense, check that everything's in agreement and you've actually answered your question. So this is literally how to do force problems in one table in your book or here in the slides, broken into 2 halves so you can actually read it. So without doing a full problem, I want to do a quick little application. So this is based off something in the book, but I'm going to do something with it a little bit differently. We have a Mars lander that is approaching the surface, so it's descending, and it is slowing down. So we've started a free body diagram by modeling our rover as a particle, and then we have drawn a vector. Now, what might that vector represent? Well, we would want to label it, and that certainly, since it's down, is probably a gravitational vector. Now note, it's on Mars, so that's going to be a little bit different than Earth, but there's still gravity. Now, next thing you want to do that wasn't done is to actually think about your coordinate system. I'm going to call this positive y hat. So over here, I'm always going to put x hat and y hat, just because it's a good habit, but this is going to be a one-dimensional problem. So this is my v vector here, but it's slowing down. What that means is that as I make my motion diagram, that my dots are going to get closer together, right? And so if this is v1, and then v2, and so on, right, now we can think about what is happening with acceleration. Is this in equilibrium? No. We see that my velocity is changing. It is getting smaller, which means that my acceleration vector is that way. Now, if my acceleration vector is that way, we know that my net force must be that way. Remember, don't put your net force vector on the free body diagram itself. It goes off to the side. So is it possibly true that we have a gravitational force down and a net force up? No, there's no way that this is possible. So there must be another force present. Now maybe it's more than one force. Maybe there's a thrust and there's air resistance. We don't know. But there's definitely one more force, and it must be up, and it must be bigger than the force of gravity, so that when you say, what is my force of gravity plus this other force, you get F net. So hopefully that makes sense. Again, we're kind of using Newton's second law here to connect acceleration and our net force to specifically, in this case, infer that there must be a force up that is in fact larger than the force of gravity down.